Hello and welcome to Call of Chemistry. This will be the fourth part of some basic concepts of chemistry series. In the third part, we ended up with vapor density of gases. In this video, we will discuss about percentage composition, empirical formula, molecular formula and stoichiometric calculation. So let's start. So percentage composition of an element in a given compound is given that mass of that element in 1 mole of the compound upon molar mass of the compound into 100. Example, suppose we have to calculate the percentage composition of iron and oxygen in Fe2O3. And given that atomic mass of iron is 55.85 and oxygen is 16. So when we solve and calculate the percentage composition of iron and oxygen in Fe2O3, we have to first find out the molar mass of Fe2O3, that is 2 into 55.85 plus 3 into 16, that is gram per mole. If we calculate that, it would be 159.7 gram per mole. So percentage composition of iron will be mass of iron in 1 mole of Fe2O3 upon molar mass of Fe2O3 into 100. So mass of iron in 1 mole of Fe2O3 is, there is 2 irons there, so 2 into 55.85 and molar mass of Fe2O3 is 159.7 gram per mole, and mass of Fe in 1 mole of Fe2O3 is 2 into 55.85 gram, and that is present in 1 mole of Fe2O3, so the unit will be gram per mole into 100. So this is cancel out, 69.94%. Similarly, percentage composition of oxygen is 3 into 16 gram per mole upon 159.7 gram per mole into 100, as in Fe2O3 3 oxygens are there, so 3 into 16 gram per mole upon 159.7 gram per mole into 100, and we get that 30.06%. This is how we calculate the percentage composition of an element in a compound. Now, what is the application of percentage composition? If percentage composition of various elements in a compound is known, its empirical formula can be determined. and from this we can obtain molecular formula if molar mass of the compound is known. We will understand this by an example. So it is given that carbon is to hydrogen is to oxygen, that is 39.9 is to 6.7 is to 53.4. First thing first, we have to divide this percentage composition individually upon the atomic mass of the elements. So in step 1, 39.9 upon 12, as the atomic mass of carbon is 12, is to 6.7 upon 1 is to 53.4 upon 16. So we get that 3.35 is to 6.7 is to 3.35. If we simplify this ratio, we can get 1 is to 2 is to 1. So from this we can find that carbon is 1, hydrogen is 2 and oxygen is 1, and hence the empirical formula, this is a trick, empirical formula will be C1 H2 and O1 whole n, and the molecular weight of this compound is given that it is 180. So it is CH2ON. Therefore, twelve plus 2 into 1 plus 16 into n is 180, as atomic mass of carbon is 12 and 2 hydrogens are there, so 2 into 1, and atomic mass of oxygen is 16, so 16 is here, into n is equal to 180. So here we can calculate the value of n. So it is 30n is equal to 180. So n is equal to 6. So therefore the molecular formula will be CH2O whole 6. Simply put the value of n here. So we get the molecular formula C6H12O6. This is how we can determine the empirical formula and molecular formula. Now we move on to the stoichiometric calculations. So there are 3 types of stoichiometric calculations. So there are 3 types of stoichiometric calculations. These are weight related calculations, weight volume related calculations, and volume. First, we discuss about the weight related calculations. For these calculations, limiting reagent concept is applied. So what is that? To understand the limiting reagent concept, we will understand by an example. Suppose this reaction N2 plus 3H2 to give 2NH3. Here it is 1 mole, it is 3 mole to give 2 moles of NH3. So here it is 28 gram, it is 6 gram. So we consider the masses of the reactants. So here we see that 6 gram of hydrogen reacts with 6 gram of nitrogen. So amount of hydrogen decides how much amount of nitrogen will react. So here the limiting reagent here is hydrogen. Basically, between the reactants, that reactant would be the limiting reagent whose amount is least among the reactants. Basically, that should be the limiting reagent whose amount is least among the reactants. So this concept is used in weight related calculations. Next, we will discuss about weight volume related calculations. Suppose we consider a reaction that is 2KCl plus 3O2. Here 2 moles of potassium chlorate gives 3 moles of oxygen. So molecular weight of potassium chlorate is 122.5 gram per mole. So 2 moles corresponds to 245 gram potassium chlorate, and 3 moles of oxygen gas is released. So at STP we know that 1 mole of gas, volume is 22.4 liter. So here 3 moles of oxygen gas released. So at STP 3 moles of O2's volume will be 22.4 into 3 liter, that is 67.2 liter. So from this weight volume calculation we can say that 245 gram of potassium chlorate gives 67.2 liter of oxygen. Next, we will discuss about volume related calculations. For this type of calculation, reactants and products all should be in gaseous state. We will understand by an example. Suppose this reaction is taken. Here carbon monoxide is 2 volume, oxygen is 1 volume, and carbon dioxide is 2 volume. Now, so at same temperature and pressure, 2 volume of carbon monoxide gas reacts with 1 volume of oxygen gas to give 2 volume of carbon dioxide. So according to Avogadro's law, we know that at same temperature and pressure, equal volume of all gases contain equal number of molecules. So here if so the temperature and pressure is fixed, so if oxygen, which is 1 volume, contains n number of molecules, then this will contain this must contain 2n number of molecules, and this also contains 2n number of molecules. So applying Avogadro's law, the volume related calculations are easily determined. So by this I am stopping here. We will discuss sufficient number of numericals in the next video. If you have any doubt, please let me know in the comment section. Please like, share and subscribe my channel. Thank you.